I marked Owen before he came, so I had a feeling he's gonna show up. Okay, well, happy Friday, everybody. It's almost, not almost, it is weekend. So let's try to remember a few things we talked about last time before we continue. Quickly, who can tell me the difference between accuracy and precision? All right, Owen.
Mostly accurate, whereas precision is more close.
You got it. Oh, yeah. So it is accuracy. I mean, how accurate it is, how close to the true it is. And then precision, how precise the data is. That means how packed it is. The repeatability every time you run it is close to the same or similar value. So that's accuracy and precision. We'll be doing a lot of that in the lab next week, calculations and discussions. Okay. When we talk about threshold and sensitivity, did we cover this or not yet? No, we don't. Okay, we didn't. We will talk about it. But can you tell me when you hear threshold, what does it mean to you? Go ahead, Gray.
Like as high as you can go.
As high as you can go. Hold that thought. Sumili? Say that again. The limit. Wait. Lazim.
I mean, it's like you cross it, like at certain points, you cross it to where, you know, like a threshold when you walk in the door, that cross the boundary to a different place.
Okay. Okay, I think you're defining it from a literacy perspective. Not Rachel, sorry, Alicia. You're saying upper and lower. Okay, let me restate the question because I think I'm confusing you. So threshold of detection. So an analysis, a method of analysis has a threshold of detection. What does it mean now to you, Tyler?
Like a effective range of like.
Okay, effective range, but really what I mean here is.
The values arbitrarily set that below which it isn't valid.
So it's the lowest value you can get that you can trust. Okay, so the threshold of detection. So some methods you have, let's say milligrams per liter is a threshold, not in nanograms. Other methods you can go as low as nanograms per milliliter, or even lower, especially if you're doing GC, for example, for flavor analysis, you can go very low and you have very low detection limits. So detection limit and threshold can be used interchangeably in food analysis or in analysis in general. Okay, sensitivity. Anybody can guess what I mean by sensitivity in an analytical method? Go ahead, Mitchell.
Does that have like radio? That's
Regularity.
more like
Granularity. Okay, hold that thought. What else? Anybody else? Sensitivity. Okay, go ahead, Owen. What did you want to say? Okay, you're cracking his hand. So I'm raising his hand. So he doesn't get a +2 for that one. Okay. So sensitivity. Let's say we are measuring the concentration in two different samples. What is the lowest difference that the analytical method can pick up? So how the sensitivity, meaning how can I differentiate between those two samples? What's the lowest difference the method can detect and consider it a different value? Okay, so is it a 0.1 milligram if a sample is different than another by 0.1 milligram, will that method detect it? Detect that small of a difference? Or it has to be 10 milligrams difference for it to detect that difference. Okay, so that's sensitivity. Okay, it's different than threshold. All right, and what case coefficient of variation is a better measure of precision than standard deviation? Remember the last exercise we did? Yes, Tina? When we compare between method, and on top of that, you have different range of the mean, the size of the mean. Because coefficient of variation corrects for the size of the mean. So when your size of the mean is, let's say 12 in one example that I gave you, and the other is 90 something, there's a huge difference in the size, almost 10 times difference. Then you correct for the size of the mean by measuring the CV, which is standard deviation, by the average divided by the average times 100. So you're correcting by the size of the mean so that you can compare precision. And if you really have a number, a value, and you have standard deviation next to it, you can't tell if the standard deviation is low enough for this method to be precise. Because when we talk about precision, we need a coefficient of variation less than 10 is good, less than 5% is excellent. How would I know? I need to calculate that. Determine if the precision is good, if the precision is excellent, if I want to really assess that precision. Okay, those grayed out is for later. They are for later. All right, let's talk a little bit about sources of errors. As you embark on your experiments starting next week, there are so many different errors we can run into. Some we call systematic error. You don't have any influence as experimental influence on them. So it's not your fault. You're working, we gave you a pipette, a mechanical pipette. We did not calibrate it for you. We didn't do a good job calibrating it. So you are dispensing what you think is 1 ml, but it's always dispensing 0.9 ml instead of that 1 ml. So it is systemically giving you the wrong volume. So your precision will be very high if you know how to pipette. Your precision will be really high, but it's inaccurate. Okay, so that's systemic error. You're something that is always happening the same way, using those pipettes not calibrated or not calibrated balance, or something that is off, an equipment that is off. It's not you as an experimenter, it's fault. Okay. Random error, that is, if Caleb is doing the experiment, then Gray is doing the experiment, they're gonna have something called experimental error, because every person might do something a little different than the other, and it's very random. So this kind of error fluctuates. And when we do statistical analysis, we take into account experimental error, which is random error, either due to technique of different people, small differences, or for example, the labs, when we do weighing of stuff, sometimes you want to measure moisture content. So you use a balance to weigh your sample. The next day after you put it in the oven, you come back to weigh your sample. If you use a different balance, you're going to introduce random error. We always tell you, use the same balance when you weigh the sample, and then when you come the next day to weigh it after drying, use the same balance. If you use a different balance, you're introducing a random error, because every balance has their own random error associated with them. Blunders. Big screw up. This happened. This example actually happened in the lab. We were titrating for determining protein content using Keldal. The last step is titration with HCl. So instead of putting in your urette HCl, put NaOH in there. So you have base. When we learn Keldal, you know that you will be titrating into a base. And then now you use base to titrate base. So you keep pouring, nothing, no change in color, nothing is happening. That is a blunder. Okay, when you use a wrong reagent, is oftentimes the issue here with the blunder, using wrong reagent, using wrong samples, mislabeling, you know, things like that is a big blunder that will impact your results. Okay. Here we go. We just explained sensitivity. Detection of only one constituent. This is not sensitivity. What is that? There's a term for measuring one thing. Specificity. Okay, so specific to one constituent. Okay. Has a very low threshold? No, not related. Low level of detection is separate from sensitivity. Detection of minor change in constituents. So between 2 or 3 samples, there's how small of a difference can be detected? That would be C then. Okay. Like I mentioned earlier, we're going to do a lot of standard curves in the lab. So the first standard curve you're going to plot is for the caffeine lab using HPLC. So basically, when you have a sample and you're after determining a certain constituent, and if you're using absorption or fluorescence or any other measurement as means of detection, we'll talk a lot about means of detection. You need to have something that relates to the concentration because you're looking to find a concentration of a specific constituent. So in order to find the concentration of specific constituents, you prepare standards. So let's say we get caffeine standards, or if we're doing carbohydrate assay, we get glucose standards. If we're doing calcium and iron determination in the atomic absorption lab, we get calcium standards and iron standards. And we prepare known concentrations ourselves. So we prepare a range, let's say 4 or 5 different concentrations. And then we run the assay, whether it is a chromatography assay measuring absorption or it's spectroscopy assay like measuring absorption. We get the absorption and we plot it. So we plot the absorption against the concentration so that we can use it to get equation of the line to determine unknown concentration. So usually when we do that, we have determined previously that there is some sort of a relationship between the concentration and the absorption. Oftentimes in food analysis, it is linear regression. So you have a linear increase in absorption when you have an increase in concentration. So then we, okay, I went ahead of myself. We construct the curve. The x-axis is always your independent variable, the concentration of your standards, independent variable. The y-axis is your dependent variable, which is the absorption. In many cases, we're measuring absorption or fluorescence. So we plot absorption is the y-axis, and then the independent variable is your concentration, which oftentimes you're looking to determine the concentration of the constituents. And then the correlation coefficient, the R, closer to 1, meaning it conforms to a straight line. Then we can say it's linear relationship. And then we determine coefficient of determination, which is the R squared, power of prediction. The higher your R squared, the more power you have in your predicting the concentration of your constituents. So usually you want to see something like this, 0.98 or 0.99. So the higher the R squared, the stronger is the prediction power. So when you use, in this example is PSA, bovine serum albumin, which is a protein. We use it as a standard for a lot of spectroscopic method to determine protein concentration. in an unknown sample. So we produce standards at different concentrations and we plot the absorption against the concentration and we get our equation of the line. Y is the absorption, X is the concentration. And then we read the absorption of the sample, we put it as Y and we solve for X. And then the higher the R squared, the more correct the X concentration is going to be. So the stronger is the prediction power. So if you have an R squared of 0.67, is this good? No. What do you do in this case? When you have an R squared of 0.6 or 0.7, what do you do? Run a different method. Or Emmeline? If you know that it is a linear, it should be linear. What would you do? More point. What else should you do, Kendall? Huh? What's that? Look for outliers. What else would you do? That's all good. But the first thing that Pam will tell you to do if you're my student, what would I tell you to do? Redo. What did you do? It must be a blunder in there. Just re-prepare your standards and run it again. And if you prepare your standards and again you have poor power of prediction, I tell you, okay, let's look at the reagents. Do you have anything expired in there? When did you prepare your reagents? Should it be fresh? We start looking at reasons why you're not getting a good R squared. Okay. Let's talk a little bit about significant figures, which is annoying. But sometimes it is really simple, but when you try to apply it in an experiment, it becomes really complicated. So a lot of what we're going to do next week in lab is talk about how you determine the significant number of significant figures in your set of data that you're collecting. How do I get this on? Huh? All right. Okay. So tell me, how many significant figures in this value? Four. All right. How many significant figures in this value? Too high?
Yeah.
Well, I don't want you to see. Okay. One. Very good. The zeros to the left don't count. If I add a zero here, 2. Very good. There you go. You remember. If I have 100, how many? 1. If I do this, just the dot, 3. Very good. If I add a 0, 4. Okay, so zeros after the decimal point, if you have a digit, then becomes significant. Here, there's no digit, so it's not significant. Okay, so you got the point, right? All right. So a lot of times we're going to solve an equation that has multiplication or division. So let's say we have a multiplication of 3654, I'm just giving you random numbers, times 238 times 1.1. And I did the math and it is 9566172. Too many, yes. Oh, nothing. Huh? Okay. Nothing. Well, nothing. That's all right. So how many significant figures I should report? Two, so very good. All right, so I would, in order to report two, what do I need to do here? So I need to round, right? So 9600. That is your value. Okay, so the reason it's two, you go with the number that has the least number of significant figures. And usually, let's say, how do I translate to a lab setting? If you are using a scale, and some scales have, you can measure down to 0.001. Some scales you can measure down to 0.1. Okay, some scales you can measure 0.001. Okay, so depending on the pipette I'm using, the scale that I'm using, all the tools that I'm using, I have to stick with the numbers that I'm certain, because that's what the balance gave me. I cannot make up numbers here. I'm not certain of these numbers. So that's why whatever this value is, it's a weight, let's say, it's coming from a balance that only read through the first decimal. So I cannot make up numbers. So I have to report to the least significant figures. All right, so yes.
Now, what if that 1.1 is like the ratio between two known things?
So, sometimes, okay, that's a good question. Actually, sometimes let's say you're taking the average and you are adding the weights that you have gotten of the 1 milliliter that you are going to do in the lab, weigh 1 milliliter 3 times 6 times. So you're adding x1 plus x2 plus x3 plus x4, 5, 6, and then you divide by 6. You don't take that into account in terms of the significant figures. You only apply the additional rule and how many significant figures you have in the top. Good question. All right, so there's a lot of if this, if that, special rule, exceptions of the rule. There are a lot of different things with significant figures will guide you along the way over the semester. So multiplication and division follow the same rule. They go with the least number of significant figures. Now I have another problem that you will face in some of the labs. So you're going to measure caffeine in different beverages. And sometimes to make sure that your sample content of caffeine fits your standard or the concentrations of your standards has to be in the middle of those at least, or within the range of your standard. So sometimes you have to dilute your sample. So let's say you diluted 50 times. How do you dilute 50 times? Usually you take 1 ml from your original Coca-Cola or whatever beverage, and you put it in a volumetric flask that is 50 ml, and you make up the volume. You put 1 ml and you add BD water. You add water to it, and that's dilution 50 times. Okay, so you measured the caffeine content using the standard curve of caffeine and using the equation of the line. You got the value of 43.5 microgram per milliliter. So this is in the diluted sample. What would it be in the original sample? What do you do to determine how much you had in the original sample? You multiply by 50 because it's diluted 50 times. So you multiply by 50. So now you get a value of 2175 microgram per ml. What would be, how many significant figures I should have? 3? 3? One. Okay, hold that thought. So it should be 1. So you end up saying it is 2000 microgram per ml. What happened to my sensitivity? Well, shut down. I brought it way down. Okay, wait a second. What am I gonna do? Come on. The volumetric flask has a specific accuracy. Okay, so this volumetric flask is accurate to 5.0 because it has an error. Can you see up here? 0.01. This is a rounded number. So always, we don't know what's here. So this is rounded. So we can say for sure that this flask is accurate to 50.0. So now if I do this, what would be my number? 3. So what would be the number? 2, 1, 8, 2180. So now I enhance my sensitivity by taking into account the accuracy of the tool I use. Okay, so this is very important, the accuracy of the tool. So a lot of what we're using in the lab, whether it's volumetric flask or volumetric pipette or mechanical pipette or a balance, they all have specific accuracy that we take into account when we record our values. Okay, so which brings me to this, I said it very fast here, rounded. So if you have a balance that can be 4 digits after the decimal. So let's say you weighed a sample and let's say it was 0.02. Okay. How many numbers after the decimal you're 100% sure of? So the balance only reads the 4th digit after the 0. So that's 4th digit is rounded. It could be 1/8 for all we know, we don't know. Okay. So this is rounded, okay? Could be 1/5, it could be 2/0, don't. So we are certain of this. This is a rounded figure. Okay, you will encounter that all in lab next week. All right, so taking into account the measuring tool or the accuracy and sensitivity of the measuring tool is a big factor in how you determine your significant figures. And that's why when I see any of my students coming to me with a table with 10 digits after the decimal, I go, wait a second. Have you thought of your significant figures? So when you report data, do not put all the decimal points you get in your calculations. Think back. And also when you report your data in a table, you want to make sure all your significant figures the same. In that column, you use the same significant figures. So that's important for you guys when you report your data. It's going to be, it will haunt you in capstone because I'm going to come to your capstone presentation and I'm going to look at every table and every number and I go, oh, what's your significant figures here? All right, so remember that. Don't hate me when I ask that question. Well, you can hate me, it's okay. All right. Good. Exceptions of the rule. Sometimes just you have a table and there's a lot of numbers and you're trying to report a lot of different numbers in the table for a publication, and your significant figures are really 4, not 3. And then we go, this is gonna be super crowded for the reader. Just make it 3. Just make your significant numbers 3 and let's go. So that we can put everything in a table. So sometimes we kind of have to go with what's meaningful, feasible, easy for the reader if you are presenting something in a presentation or in a manuscript and so. Make note of updating the pages. Maybe in what I posted, we had old pages numbers, just because it was carried over from the first edition. So, so we touched with significant figures. You can also reject a data point. So I think we talked about very, very briefly last time is when you have 3 replications. That's why I tell my students minimum is 3 replication, no matter what. But sometimes we need to do 5, 6, 10, depending on the complexity of the method. But never 2. Unless you have always good precision, and we can go with 2. Because sometimes there's a mess up and you look at the data and you go, this 3rd rep doesn't make sense. It's screwing my data, it's increasing my CV, it's, messing with my accuracy. So we can eliminate it. You mean you don't want to eyeball it and say, okay, delete. No, we don't want to do that. You want to actually do it with a statistical way, and that would be determining the Q value. So the way you do that, when you look at your replication and you really have in your gut feeling, this rep is messing me up, messing all my data. So what you would do is you would take that data point, X1, let's say, and then say it's further from everything else. I'll take the difference between this data point and the one that is closest to it. Okay, so this would be absolute value really. So X2 minus X1. So the data that is most close to it, you take the difference. And then you divide by the range of the data, meaning the minimum value. Maximum value, subtract from it the minimum value. That's the range of your data. And you get a calculated Q. Now in your book on page 48, hope I got that page right. There is a table 4.4. It gives you the tabulated Q values. And you would say, what are the number of observations? Let's say you have 3 observations, and then it says Q of rejection 90% level. So you can choose your confidence level. You can go with 90%, oftentimes is 90%, not 95. And then you get that number 0.94. If your calculated is greater than the tabulated, you say, yes, I can remove that replication. Throw it out, move on. If you have 2 reps only, you don't know. If they're very different, what should you do? Add a rep only? Redo the experiment. Redo the experiment and do 3 reps. Yeah. Okay, so next week in lab, you're going to, very simple lab, you're going to work with only water and different tools of measurement. And you're going to do repeated measurements using different tools and measure precision and accuracy. Some of you might think of it that this is just way too dumb for me because I've been in labs, I know how to use it. Bear with us, consider it an exercise, and just to look at data together and look at accuracy and precision. This will carry forward with all future labs, this accuracy and precision. So some of you have used mechanical pipette once, some of you have never used it. So it's good exercise and kind of ease you into the labs, really. So read chapter 4 in the book or the slides or the recording, and chapter 6 in your lab manual. There's also a lab safety sheet and sources of error sheet on the Canvas in the top welcome section under lab information and guide. Of course, pre-lab quiz by 9 a.m. Please bring your lab manual, physical copy, or a printout of the chapter. We need your laptops. You're going to be entering data. I'm going to send you an email with the Excel sheet that you're going to be using to enter data. So bring your laptops and lab notebook. You need your laptops, not necessarily a calculator. Just you'll do the calculations all via Excel. And please try to come 5 minutes early. You're going to be selecting a lab code, putting your name tag on it, getting ready. So if you're able to come at 9:30, that's 5 minutes before the start of the lab, that would be great. Okay, any questions? All right, I'm going to start a new topic in the question.
So about plants and I'm going to really water, but do you like normal have kind of clothes?
Yeah, so we're gonna talk about safety in the lab next week, but Jenna, thank you for asking ahead of time. It's still summer and we're probably wearing open toes, shoes, please don't. And no shorts, and you're gonna be wearing lab coats, so it's okay if you're not wearing like sleeveless, if you're wearing sleeveless shirt. But no shorts, no sandals, ladies with long hair or guys with long hair. Or individuals with long hair, just keep the hair back, like, in a hairband. And let's see, no water or food in the lab. We'll have a table outside to put your water bottle. So this is general. Thank you, Kristen, for asking. All right. All right, we move on. I'll start the next chapter. We won't go too far, but we'll just introduce the topic. So, okay, this is the last boring topic. I mean, all of those chapters are introductory, and I know they're not much excitement there, but they're very essential. We really need to know these essential topics before moving on. So sampling and sample preparation, very essential in food analysis. Can anybody tell me why this is essential, you think? What do you mean? What do you understand when you say sampling? What does that mean to you? Yes, Rob?
Got 100,000 of a product and you need to know that most of it's pretty good and you can't open 100,000 of your product.
Simply put, yes, you need to take a representative sample of the population. So you have a population, whether it is 100 bags of flour or 200,000 cans of tomato soup. So whatever is your product, you have a population. And you need to take a representative sample. And there are rules for taking representative samples and numbers of samples. Okay, so we're going to talk about what do we mean by representative sample and what procedures we do for sampling, and also how do we prepare our samples for analysis? Because if we mess up in any of these steps, we might risk the safety of the consumer by accepting a product that has Clostridium botulinum, for example, in it. Or we might reject the product and throw away the whole lot and cause thousands upon thousands of dollars lost for the production, for the company. So there is consumer risk and there's vendor risk. And if we mess up sampling and sample preparation and have the wrong results, that is the worst thing that can ever happen. So no matter how boring this topic is, it's very essential in food analysis. Okay. Let's see. To determine food quality and acceptance, it is essential to read for yourself and tell me what you think. Ina? All of the above. Anybody with similar or different answer? Mitchell? It's B and C. A is when you have a whole lot, like we say 1,000 ton of flour or 200,000 cans. We're not gonna able to measure the whole lot or the whole population. We have to take a representative sample. And here, when I say sample size, determine sample size, it doesn't mean the dimension or the weight or the volume. It means how many samples you pull up. 10 samples, 12 samples. That's what I mean when I say sample size. It's not dimension, it's number of samples. Okay. So, is it feasible, the answer, to evaluate all food or ingredients from a particular lot? Like, look at, this is a container full of wheat or any grain, and you have, I don't know, several tons. What do we do? No. Is there any, okay, go ahead. We grab small samples, but is there anything that can be done on the entire lot? Go ahead. Aha, thank you, Elijah. Yes, so when you're looking for metal contamination, you can run the entire sample on a belt. You have a magnet on top to detect metal and actually grab that metal out of your sample. So that could happen. Rapid analytical technique, non-destructive, goes through, determine, let's say, color or metal contamination or any other non-destructive type of look at the quality, basically. But oftentimes we have to sample. We take several samples representative of the entire population. So we're going to spend time talking about what do we mean by representative? How do we determine that this is representative of the entire population? Try to get accurate estimation of how many samples we need to get for a particular set of sample or a population. The more samples you take out, so the larger the sample size, 10 versus 5, the more sampling you do, you reduce the variance. Next week in lab, you're going to see the difference between 3 replication and 6 replication. The more you replicate, you reduce the coefficient of variation. And then you should have a sampling plan. So I put it in red because I need you to be able to define a sampling plan. What is a sampling plan? Anybody can guess what a sampling plan means? Go ahead, Rachel.
Amount of samples that we can do for the timing of the focus.
That's part of your sampling plan. So first of all, you want to say, okay, how many samples do I need? How do I sample? How do I pull out samples? So sampling plan include determining the sample size, then determining how am I going to pull out samples, then determining how I'm going to prepare my samples and store them before the analysis. Third, if I'm transporting the samples to the lab, how am I going to transport those samples to the lab that can analyze them? So it's a whole process. So your sampling plan is a whole process. It's not just taking out sample. So really, sample size, sampling procedure, how am I preparing the sample, storage and transportation. All of this goes into the sampling plan. There is this table, 5.1. Of course, I don't expect you to memorize, but at least to be able to look at it and, you know, think about it and say, oh, that makes sense. But I want you to be able to define sampling plan. That's why I put it in red. You're responsible to understand what a sampling plan is. And here, some of these factors that impact your choice of a sampling plan are intuitive, right? So what is the purpose? am I sampling to accept or reject the lot? So this is often when you're looking at a particular characteristics, is there a defect or number of defects that makes this lot not acceptable to the consumer? So I would have to make the decision based on that to determine my sample size and how I'm going to take out representative samples. Am I looking at average quality? So am I looking at total fat content, or am I doing this to look at nutrition label? If I'm doing this to look at nutrition label, there are FDA and FSIS have specific rules for sampling, and I'll give you an example. So nature of the product, is it homogeneous? Am I looking at milk, for example, that has been homogenized? I don't need to do anything, it's very easy. Or am I looking at a product that is not homogeneous in nature? So it has multiple layers, it's not consistent. So sampling would be impacted from such a heterogeneous product. What is the unit size? Is it like cans of 100 milliliter soup, or is it a truckload of grains? So what is it? And then also, what is the cost of the material being sampled? That will impact how many samples I'm gonna pull out, amount of the sample prep, all of that. Is it a critical assay or not critical? Will someone become sick? This makes it a critical assay. Is the test destructive or non-destructive? That means if it's non-destructive, I can use the sample for multiple tests. So let's say go through NIR and determine composition. I can take the sample out and use it for something else. And so on. So you can look at the table and just try to, sometimes I tell you, give me an example. Just you can take that table and pull out what you can easy to remember, make sense, and then you can give an example answering a question. All right. Gosh, I'm losing most of you. So I'm gonna stop a minute early. So have a great weekend and I'll see you on Monday.